Okay, it's my pleasure to introduce Jiachang Xu, who will talk about non-Archimedean uniformization and its application.
Thank you. So thank you for inviting me to give a talk here. So today I will introduce you the basic idea of kinetic actually the non-Archimedean uniformizations with this is work of Mumford and Mastaffin, and I will talk about some still actually still working in progress and struggling inside if I have time. So let me first start from the classical complex and uniformization. So for an unit curve, so E is an unit curve over C. Okay. So we know that if we consider the complex point of this, it's a closed point of this unit curve. So we have a very classical result that is this guy could be represented by as a complex torque, where it's tau. This guy is it's a lattice, which is located inside the convex band. So he directs on the tau with the image part of the tau is equal to 0. So this is a basic result for the unit curve in the complex sense. So if we increase the dimension, so we will get a Abelian variety. That will give us the identification functor will give us if we have Abelian varieties with dimension g. So it's a complex Abelian varieties with the dimension g. Dimension is equal to g. We have if we use the identification functor on it, we will have a complex source with the dimension g. With dimension g. But this functor, actually in the dimension 1 case, we know that this two sides with dimension is equal to 1. So we know that this two category is equivalent. But unfortunately, if we increase the dimension into the Abelian variety case, this is just a faithful, fully and faithful functor. So that means not all the complex torque could be an Abelian variety. So now there's a natural question. That is, if we consider the questions, so if we consider the unit curve over a non-Archimedean field, for example, let's consider the most classical non-Archimedean field in P. So the natural question is, if we have the Semmer element construction such that in general we will ask that if we take the CP point, or actually here we can take any finite extension of QP if you want to the Semmer case. So if we want to eat this guy, is we can find the isomorphisms on each side. We have so find CP modulo a lattice inside the CP. So it's similar like that. But unfortunately, this is not true because we know the lattice we can always consider it as a discrete group. But in the CP, it's very hard to find a discrete group. Because if you consider any subgroup which is generated by an element inside CP, for example, if you pick up any B, it is belong to CP, and we consider this submodule C, ZP and VP, and you will see that this guy, the sequence located inside this, for example, if we consider PK, this guy will converge to 0. So it's so 0 point is an accumulation point inside this module. So it's not discrete. But fortunate thing is type find this thing that is in a complex case we have a isomorphisms from the C modulo V and we have this if we consider the morphism as exponential 2 pi I tau to C modulo which this guy is the classical complex uniformization. It's C. So here C is elliptic curve over C. So that means if we can find a similar thing to represent the CP point of the elliptic curve of the CP point of the elliptic curve over QP, we call that as a uniformization. So that means we need to find CP. This is the unit of a CP modulo Q, where Q is belong to the unit of CP, such that Q is smaller than 0, and type proves that we have, if for the fixed Q, we have EQ. So the EQ is it's an elliptic curve over QP. We have the CP point of this guy. It's isomorphic to CP, the unit of CP, modulo QZ, where Q is the element on this. So now we can see this part on this side. On this side, actually on this side, we call it a p-adic uniformization for the EQ. And this guy, in this part, we can use the so-called regional variety to there's a regional group and not a structure on the CP point of this EQ. And but EQ itself, it's algebraic one. It's an algebraic curve. It's a traditional classical elliptic curve over QP. Okay, so let me explain that. What's a rough idea how we can do such kind of uniformization? So first thing, we claim that so this thing has a generalized addition. That is, if you consider any k as any k, if you consider any k as a non-Archimedean field. So here is you in general we assume it's complete with respect to the norms which induced by the valuations on this field. And this is non-Archimedean field, complete non-Archimedean field. So we have we can define the type curve. It's a one-dimensional non-Archimedean projected curve. It's a rigid analytic curve, which is defined as J is T is defined as the non-Archimedean. Okay, so here AN means the non-Archimedean amplification, and the modulo is the Q. Okay, so the idea is from here. So if we consider the
sorry, what is this G and K?
Oh, it's the algebraic Tor. It's
the algebraic Tor over K. Right?
Yeah, over K. It's algebraic Tor over K. And here AN, if you don't like AN, you can replace here as if you want to replace this as with the complex amplification. So this here is the rigid amplification. So we have a similar Gauss series between the algebraic varieties over K, where K is a non-Archimedean field, to the rigid analytical varieties over K. So here in this talk I will not use the formal definition of rigid analytical variety, but you can consider it as it's a counterpart of a complex manifold in the non-Archimedean field. So, sorry. Here's here.
And the rigid analytic structure means that the deformations of the analytic structure.
Oh no, it's a different thing. It's different thing. It's different thing. It's there are two kind of viewpoint of rigid analytic variety. The one is it's original one, which is defined by type. That is means locally you can consider it as the section of this varieties you can consider as a p-adic convergent formal power series. It's like that. We call it Taylor algebra.
Okay. Why is it rigid? Where does the rigidity come from?
I'm not very sure about this where it come from, but yeah, yeah. But the only thing I can tell you that this is a difference with rigidity in the algebraic geometry. That's a different thing. Yeah. Yeah. There's another point is to view this guy is by Reynolds saying is that any rigid variety, the category of rigid variety could be considered as the formal scheme, which and quotient out the birational. So you can consider the rigid analytic variety as a formal scheme, but it's up to the birational thing. It's a formal thing over the dB over evaluation ring, and if you consider the function field of this formal scheme, if they are birational, they will get the same rigid analytic variety. Okay, so here is the thing. If for the elliptic curve, over so here you first consider over QP, or you can just think about this guy as located inside C. So we have the Weierstrass equation of this elliptic curve. That is so let me write the equation here. It's y plus xy and equal to x cubed and plus a4qx and plus a6q. So the coefficient about q is so here a4 and a6q are both located inside the ideal of a formal power series generated by Q. So in this side, we have, you can think about this guy when you consider the full, in the complex case, we have, we can define this guy, because this is our formal power series, so this also works inside the non-Archimedean field. It's a valuation field. You can also think about the convergence things inside that field. So, so this thing, the isomorphic is come from the GM CP. So this is torus over CP, algebraic torque, and do the amplification. QV, we will get the isomorphic constructed by type. It's EQCP. So it's for U, which is defined assigned to the pair XUQ and YUQ. So here XUQ and YUQ are both the formal power series over about U and Q invariant. But this is the same things come from the complex case, because this is a formal power series, so this is also works inside CP. So this is how the type originally think about using the non-Archimedean torque quotient out of QZ to get the CP point of the elliptic curve of over QP. So unfortunately, it's unlike the complex case. So in the complex case, that we know that for any elliptic curve we have a complex uniformization. But in the non-Archimedean case, this is not true. And I prove that if we have a elliptic curve QP such that we can find, so here Q such that the EQCP is isomorphic to for any elliptic curve E over QP, if we can find a EQ such as this guy is isomorphic to G and CP unification for QN. So we call that this E have a p-adic uniformization. And this.
Sorry, I have a question. So this ECP, is it just base change to?
No, it's not base change. It's CP point.
To the closure or algebraic closure of QP.
And the completion.
Yeah, and the completion.
Yeah, it's a CP point. It's a
yeah. Okay.
Yeah. It's just CP point. If you want to use a network scheme, it's like the spec. It's a home set of. So here is a QP, and here you can spec of CP2 like this. So also you can consider is this guy as there's a generalized result is that for any rigid analytic variety, the closed point of this rigid analytic variety is theoretically is a bijection to the closed point of the algebraic variety itself. So this is you can consider this guy as a closed point of the E over QP because CP is both complete and algebraic closed. And so if E is isomorphic to EQ, we say that this E has a p-adic uniformization, which is we have an additional condition on this E, that is U must have split multiplication. Multiplicative reduction. So I don't want to formally introduce this. This means that if we have because E is you can consider the algebraic varieties over QP, and you can find a formal model of this guy. If we find a formal model of this guy is located on should be if it's CP, we should consider the corresponding to dBr of the QP. So it's this guy it's curl over ZP. And the reduction of this guy, that will give us, you consider the special fiber of this formal scheme, so that you will get algebraic curves over the FP. So for that curve, we have a split multiplicative reduction, means in that curve, in that reduction, the singularities inside the reduction is only at most the ordinary double point. It's just nodal. And also, it's a stable curve. And there's another condition that is the normalization of the component that should be rational. So that's a series, at least, of a condition to guarantee this has a p-adic uniformization. So this is dimension 1 case. So there are two kinds of generalization. That is generalization of the. So it's there's a two direction. The first one is goes to higher genesis. Goes to with G is greater or equal than 2 in this case. And another thing is we need to think about if we can increase the dimension of this to the varieties, not only higher dimensional case. So let me first give you the result, which is by Mumford. So it said that if we have a net gamma, which is a Stokes group. Actually, this is kind of discrete and topological finiteness condition. Group of PGL MK, PGL 2K. So it's a curve case, and then there's a p-adic unification. That is, we can, for this group gammas, we can find a. So here is another rigid analytic varieties associated with this gamma. I will give you an example later. And modulo this group action itself. And you can always find a algebraic projective algebraic curve with genus G, such that x gamma, such that the point of the CP point of this guy is isomorphic. So here is we assume all the here K we consider it as a QP. Okay, and so let's see the simplest case of Mumford saying that. So here, gamma in the Stokes group means this guy, the action of gammas is Fourier portion finite generated and discrete. So this is a similar definition of the arithmetic groups. And this guy, the domain, the fundamental domain omega gamma, which is defined as a CP point of P1 and minus the limit point of this guy, L. We use L gamma to represent it. And the simplest case example is if you consider the K as QP and we pick up an element, for example, if we pick up an element which is generated by the matrix of Q, 0, 1, 0, with the absolute value of Q is smaller than 1. And we generated this Q as, if we think about it, if we net this gammas, which is generated by this guy, and after some calculations, you will find that the limitation point of this gamma is just a 0 and infinity point. So it's just these 2 points. So in this case, you can calculate that this guy is only the 0 and infinity point. So in this case, if you use the P1 CP point minus 0 and infinity point, then you will get the unit of the CP. So, and the gamma itself is gamma Z. So in this case, you can see we get the omega gamma is just the P1 CP minus the limitation point, that's just the CP unit, and modulo the gamma. So this is just a type curve. Okay, so now I will introduce you something about the higher dimensional case. So before introduce the higher dimensional case, we need to introduce we will use a series of Bahati disputing. Or Bahati street. So first, this guy could be defined on any discrete evaluation field. But let's consider the case of. Let's consider the simplest case to give you some impressions of these things. That is, if we consider K with QP and the associated DBR is the DP, and the related field is should be the simplest So here V, it's it's a QP vector space with a dimension. Let's assume the dimension is n+1. Okay, so here we just consider n is equal to 2. Let's consider the projective line case. And then we can define the nacus inside this guy. The nacus inside this guy is the ZP module with the rank 2, with the rank 2. So you can see that if we pick up any nacus n inside this guy, it could be generated by something like the ZP1 and plus ZP into like this, and where E1 and E2 are the linear independent vector inside the ZP. So now we can, there is a thing that is let's see. So okay, so then let's first define these trees associated to the PGL QE. So here we already fixed a vector space V with a coefficient QP and dimension 2, and then we need to define that the equivalent equations of this lattice. If we have two lattices M and M prime, we define this guy. If we can find there exists. If there exists a lambda which is belong to QP cross, such that M is equal to lambda M prime. So if we have this kind of relation, so we call this as M is equivalent to M prime. Then we define the equivalent class of M, which is I use this guy to represent it. Now we need to show that there's a tree associated to this projective general linear group, and if we have two lattice equivalent class, so this guy is then there exists. So we associate each lattice equivalent as a vertex. So inside the tree, and we need to define for each vertex how to define there's an edge between these two vertices. That is, if there's an edge between this guy to this guy, if and only if we actually define the distance of edge and prime equal to 1. So let me explain what this means. So the distance means, so if you can, for here you can always, for any two ZP lattices inside the vector space of QP with dimension 2, you can always assume that M, we consider the M is contained with M prime, such that the M modulo M prime, this guy, by the basic algebraic structure theory of a module over a PID, you will get this guy is just the VP modulo the P with some power 1 and sorry here, this modulo ZP2 is like this. We have a structure theory. And we define the distance between M and M prime. Actually, this is representative of the lattice class. And so M and prime is defined as the absolute value of E1 minus E2. So when this difference between E1 and E2 is equal to 1, we say that there's an edge between these two vertices. So let me calculate a concrete example for you. So let's see.
Sorry, can you explain again what is M parenthesis, that correspondence, vertex?
Oh,
yeah.
So here, let's start from, go back to here.
Yeah.
We have a vector space with a GOP coefficient to dimension 2. And this guy we can define the lattice of, that is a ZP module with a rank 2. And for each lattice, we define a equivalent relation. That is, if we can find a non-zero QP such that the two lattices are at this relation, we say that that's the equivalent.
This is equivalence relation with it's not with respect to a lattice, it's a general equivalence relation. You don't need to fix a lattice.
Yeah, we don't need to. Yeah. And for each equivalent class, we assign a vertex. And for each two lattice class, we assign an edge between these two vertices if the distance between these two lattices is equal to 1, if and only if. So here is another point to explain that is we need to think about if we fix the so if we fix a vertex M, so let's pick up a representative lattice class. How many edges of this we will connect it to this? So actually, by that means, if you do some concrete calculation, you will see that this guy, because this guy only is not dependent on representative. You can always choose a good representative. So such that it looks like this. It's M. For example, if we pick up M as is a standard case, is the E1 direct sum of ZP2 and M prime with this two. We can always choose this guy as ZPP E1 direct sum of ZP2 like this. This is a very good position for these two lattices if you choose a good representative of the equivalent lattice. So in this case, that will tell you that the edge connected to this guy is a one-to-one corresponding to the M prime let me see, it's M prime to the Pn. So, but this guy is one-to-one corresponding to the P1, the P squared. Okay. Oh, sorry. Here should be FP squared. FP squared. Because this guy is contained inside the M modulo and P like this, and M is rank 2. So
what is Pn?
Pn is a user. We choose the prime number P to multiply the lattice. So this guy is isomorphic to
It looks like a capital P, whereas there it looks like a small p. So
oh, sorry. Yeah. So you will see that the line inside FP2 is corresponding to the edge of that guy. So if you do the counting thing, that when you choose P equal to 2 and we consider PGL to Q2, the simple case you will find that if this is vertex M, and you can only find a 3-point to connect this, because the point of this projective space is only 3-point. It's like this. So this is a standard picture. You can search it online. This is a Bahati trees for this is the simplest case. So it's like this. So like here, if you pick up this point A, this point B, So we call that the distance between A and B is 1. And if you consider this point C, you will see that the distance between A and C is 1, so the distance between C and B is 2. And so you may ask how many points connected to the point B inside the tree with distance 2. That is you can just consider the m prime modulo p square m, which is 1-to-1 correspond to the p1 z modulo p square, and the square like this. And also you will find this tree is an infinity tree if you take the limitation of p, if you take the inverse limitation of p. So the boundary of this point will correspond to, if you take the limitation of this guy, that will give you the p1 vp. Okay, so we have so now this is so in the higher dimensional case, we can still define the Stelmach-Stokes group, which is belong to it's a subgroup of PGF and +1, QP, and you can define the Stelmach-Stokes condition and finally generate torsion-free and co-complex, which so that must not be to prove that for each gamma, we can associate to a rigid analytic variety omega gamma, and such that you can find after quotient out this group itself, you can find algebraic varieties, projected algebraic varieties. So this is higher dimension also true, and also we need some generation condition on this guy. This is not the most important thing we are going to use. And the most important thing we're going to use is we always interested if we choose the proper gamma group, the omega, we will always want to, so here the thing each gamma, we can construct a projective formal scheme. It's a P delta gamma. And if you take the generic point of this guy, generic point of this guy, so you will get the omega gamma. But we are more interested in how about if we choose the proper gamma such that this delta gamma, this is the convex subcomplex of the Bahati tree. If this guy is equal to Bahati tree, this is the most interesting case in my work. So the thing is that so this is in this case you can see that this is infinity tree, and you may consider that for each vertex, so if you use the tree to represent the Bahati tree associated to the PGL, if you consider higher dimension, or you can consider any non-linear field. In general, you consider the discrete value field. And so you may ask, what's this? Well, you may ask, how about this stuff? If the delta here is if the delta gamma is equal to the Bahati tree, it's a Bahati tree. of associated to the PGL n plus 1 QP. And you will see that this guy, how can we define this guy? So here's from this thing. If we have two vertices, here's M, and here's M prime. Okay. So now we know that this guy M is a ZP module with a rank n, right? It's a rank n plus 1. It's a rank n plus 1, and we can do the project construction for this guy. So I mean, there's for this guy there's associated PM. So more precisely, it's a proj of DP symmetry of this lattice, this guy. And here, M prime, we can also have such kind of construction. And for the edge, we define as.
Sorry, what do I take the project construction of? I have a rank, I have a dimension in.
So project construction is that locally.
What's inside the project construction?
It's a symmetric
it's a
algebra.
symmetry.
Symmetric algebra.
Symmetric algebra. So the symmetric case, if you consider the vector space, you know that it's a finite dimension, and you will get to the standard projective space with dimension n, right? Okay, so now we can define the associated projective space associated here is Pm and the Pm prime, such that so here's the rho and here's rho prime, and we define as the P M prime is defined as the image of so here's the prime. The image of because we can choose the proper lattice such that M prime is sub-lattice M. So we have a induced morphism from Pm to Pm prime. So we define this guy as the image of this morphism located inside the product of this two things. Located the image of this guy. This is not commutative, sorry. So you can we can use another morphism F. It's the image of F, which is contained inside the Pm cross Pm prime. But by the local calculation, you will see that this guy is just the blowing up of this projective scheme along the. So in our example, this guy Pm prime, it's a blowing up of locally. If you choose a proper coordinate, it's if we consider this guy as x1 and P with the associated closed subscheme Pm, like this. So here is not a homogeneous coordinate because I just do the local calculation. You will see this if you choose an affine chart of that guy.
And M prime is contained in
Yeah. We choose the proper because there's an edge between M and M prime, so we can choose properties such that M prime is the sublattice of M.
So, but this map can be only birational F.
Yeah. It's a birational. Yeah, that's right. It's a birational. And this is just two. Yes, you're right. It's birational. So this is just for this case if you pick up 2 point M and M prime. And for the another point, you can also do this kind of construction. You will find all these things will constitute of a projective limited system. And if you do that limitation, you will finally you will find that if you do that limitation, you will find that the final projective, the generic fiber of this guy, the generic fiber of P, this is about T3 associated to PGL and plus 1 QP. And this is the formal scheme, and let's take the generic fiber of it. So this guy is Pn, sorry, here's QP, PNQP, and removed the union of all the QP rational hyperplane. H is a belong to H. And here H is all the QP rational hyperplane inside this. And more precisely, this guy, you should consider this guy as a ridge identification of the projective space with dimension n, and remove all the QP rational hyperplane. This is a very good thing. We call this the germ-free upper half space. So why we need this? Okay, we have 50 minutes.
So sorry, what is the connection of these approach constructions with the generic fiber?
Okay, so here, this guy is, if you don't like the formal scheme, this guy, all these things are just as a scheme over the DVR, right? Because M is a ZP module, so this is the projective scheme over the ZP. So all these things is if you do the limitation, you will get a scheme over ZP over DP. And for a formal scheme, if you take the generic fiber, because this guy is, you can consider this guy, X is over the SPF ZP. So this is DVR. So this guy has 2 points inside. If you take the generic fiber of this guy, you will get an original variety over QP.
So what is curly X in this case, the total space, what is it in terms of this approach construction?
The cardinality of this?
No. You introduced the approach construction.
Yeah.
Of these lattices or modules, and yeah. So what is the connection with curly X and what you described in this approach construction? I mean, for any pair of modules ordered by inclusion, you introduce approach construction and maps, birational maps, and proper maps, and one birational map. What is the connection of all this with the rest?
With the rest, each time you will also get, you mean if you do the final step of below itself, like that? So each time you will get a scheme over ZP and such as the generic, because the function field is always the PK1, the PKN, and you will see the special fiber of each one is just has 2 components, and each component, the singularity appeared to each component is just at the most the ordinary double point is like that.
So you have a sequence of modules?
We have a sequence.
Birational maps?
Corresponding
birational maps?
Yeah.
There is some improvement of this special fiber going on, or what's the point of this sequence?
You mean the other point is when the distance with n like that? Oh, you mean because if you can still add another point, and
yes.
we just do the below sum again like that.
Yeah. Okay.
Yeah. So okay. So we can talk about after this talk. Okay. So recently there's a work, we have 10 minutes to quickly introduce you the mirror symmetry, and if we have a complex abelian variety CA, this is complex abelian variety, and then we consider the ample cone, which is located in the narrow severe group. We consider the CA, CA ample. let's use the original notation. This guy is RA. And we do the complexification. That will give us the CA, which is defined as CA plus, and this one union with CA minus, where CA plus, which is defined as narrow severe group of A, and plus, so here's a plus or minus I times and we'll close. So here's a matter with the notation and the dimension here. So now in the Long's paper they prove this result. The following result, that is so for any abelian variety, complex over complex field, and omega A, where omega A is an element to belong to the CA we define here. So then, if we have two, we call this an algebraic pair. And if we have a three pair, if we can have A and B, we defined omega B and C, omega C. So those all the ABC are all abelian variety over C. And we defined a mirror symmetry condition among them, such as A, omega A is a mirror symmetry with the C omega C, and the B, omega B is mirror symmetry with the omega C. Then we have the derived category of this abelian variety A should be equivalent to the derived category of coherent sheaf of the abelian variety B. And for each A and for here A and B are mirror symmetry, that we'll explain this later. Mirror symmetry with the C. With the C. Okay. So now let me explain this how to roughly define this mirror symmetry means that, so here we already defined the complexified ample column for each abelian varieties. And the one thing is that there's a result that you will see that the CA plus and the CA minus are both Hermite symmetry domain inside the complex space. So by the Denis work, we know that every Hermite symmetry domain could be considered as a parameterizing space of variation of the whole structure. So they defined that for each fibers, so here omega A, so let's see this. So let's consider this guy is a Hermite symmetry domain. And if you pick up an omega belong to here, you can think about there's an whole structure, and there's an R whole structure over here. And for each abelian variety, there's a canonic, it's polarized R whole structure with weight 1, the negative 1, 0, and 0, negative 1 abelian structure, such that they are as there's a definition. It's a kind of a commutative properties with this whole structure defined here. So we call that it's a mirror symmetry relation. If we have for this B, we can also get a CB plus, and this guy is also Hermite symmetry domain, and you will get a variation of the whole structure over it. And we can define the mirror symmetry. It's a commutative relation between these two. Between the matrix, actually because we can do the complex uniformization for any complex abelian varieties, then there is
So what about B? Did you have something explicit for B, or what property?
B is both ABC are all abelian
All
variable.
are abelian, okay.
And
so your symmetric is again abelian. Right?
yeah. So, oh no, these three are already true. If we have three abelian varieties, and each three we have a corresponding complexified ample column of each of abelian varieties, and each complex ample column is a moduli space of a whole structure. And for if it's two abelian varieties, if we have magnitudes, if you have isomorphic, let me roughly explain here. If this gamma A is expand matrix which uniformize the abelian varieties. This group of abelian varieties goes to the gamma B direct sum of gamma B hat, and because the canonical complex structure associated to the abelian variety will associate to a complex structure of this type. And also the whole structure is also, you can define whole structure on this side. There's something kind of a commutative condition properties in here. We define as these two complex abelian variety are symmetry, are mirror symmetry. So if their whole structure satisfies a certain commutative condition, we call these two things are mirror symmetry. Once they have a common mirror symmetry C, omega C, their derived category of Taurus sheaf are equivalent. So the thing is, you may think about it, there's an example, if you consider the simplest case, it's an elliptic curve CE, it's an elliptic curve C. So you will see that the CE plus is just the classical half plane. It's a classical upper half plane. So if you see it's just this guy, it's a C minus R. You can do the calculation, and you know this guy. It's just a set of parameterized whole structure of on the R2 with negative 1, 0, and 0, negative 1, 1, 0, and 0, 1. So you may think about if we replace the E by the tight curve over QP. So the naive thinking is because we want to define the associated complex ample code for the algebraic varieties over the non-Canadian field. But in that field, you cannot do the direct. You cannot do this because if you do this, obviously, if you replace the C by the CP, obviously that guy is it's not a parameterizing of the proper whole structure. So that means we need to find the proper modular space of a whole structure associated to the algebraic associated to the elliptic curve EQ. So the naive thinking is that this guy, the non-Canadian correspondent inside here should be the Drinfeld upper half plane. Because in this case, if you take the CP point, you will see that if you take n equal to 1, you will see this guy is just the P1 CP remove the point P1 QP. So this is a natural analog of the classical half plane. And the good thing is that this guy is, in the PID world, this guy is a parameterizing space of the isocrystal. That means this is the simplest case for the parameterizing space of the PID whole series. But on the higher dimensional case, this is not good. If you consider the two elliptic curves cross together, you will get the saddle upper half plane, and it's not easy to find the p-adic analog of saddle upper half plane. So the thing is that we are working on to do this to you can consider two, because for each Hermite symmetric domain, that means they give a corresponding Shimura corrected data. So what we want to do is to extend the mirror symmetry condition to the corrected symmetry, corrected Shimura data. And once we use the arithmetic group to quotient the Hermite symmetry domain, we will get a arithmetic breadth over QP. And then there's another work by Yakov in Israel, and they have a result that for proper arithmetic group quotient, you can get a p-adic uniformization by the dream-free upper half space. So I think that's a possible way for us to find the correction between the classical Hall structure and the PLK Hall structure. Okay, so I don't have time. I think that we should stop here today.
Any questions? I had a comment and a question.
Okay.
The comment was about rigid, where it comes from. Is that when Tate was trying to define sheaves on analytic varieties over p-adic numbers, he didn't have enough sections. So this is why he wanted to rigidify the sheaves structure. This is why he went to G topologies.
Yeah.
So this is what the term rigid comes from.
Okay.
Not from rigid diff, from rigid spaces that
Yeah.
don't have any non-zero deformations. The second question I had was, seeing these constructions with Bruatit's trees and also this rigid analytic setting made me think that this could also be done in Berkovich.
Yeah. I think so. I think so. It also works in the Berkovich setting.
Okay, and it has been done. Right?
Yeah. There's some kind of works by, I can't remember. It's a French mathematician. They find the correction. They can embed the Berkovich tree into the Berkovich identification of the space itself. So it could be considered as a kind of chocolation and a skeleton of that space. So yeah.
Okay, so it's a big, okay.
Yeah, it's a very similar to that part of it.
Okay.
Other questions? Well, if not, let's thank our speaker again.
Thank you.